Today I will talk to you about my work in discovering the most distant solar twins for the purpose of testing fundamental physics. And we try to get these stars with HERMES, which is the same instrument that the GALAH survey uses. So first off, let's go to our motivation. So we want to get the most distant solar twins known today to probe fundamental physics, in this case, the strength of electromagnetism, which is often denoted as the fine structure constant alpha. And this is mainly the work of Daniel Berkey, who is another PhD student here, who has achieved that we can measure the fine structure constant very precisely in solar twins. Here, 10 to the power of -7 in delta alpha over alpha. And we want to have an underlying physical effect that causes these potential changes. So we try to map out alpha against dark matter density. Here on the right, you can see a dark matter density profile of our galaxy. The most dark matter is obviously in the middle, and we try to probe for solar twins that are way further in, about 4 kiloparsec further in than the sun, in order to find the differences there. So now the big problem is that we can't just go to a big telescope like the VLT and try to observe solar twins, because that's time intensive, and we don't actually know solar twins that are that far away. The furthest solar twins that we know are about 800 parsec away. And the reason for that is quite simply, solar twins become very faint when we move them that far away. Solar twins have about a G magnitude of 70.4 when we move them at our target distance of 4 kiloparsec. So with HERMES, it's a little bit simpler. We can have a lot of targets at the same time, and we can photometrically pre-select solar twin targets with Gaia, which means that we can efficiently observe these solar twins. And we think that we can get a signal-to-noise ratio of about 25 on our faintest targets there, which means that our challenge is to use these low signal-to-noise ratios HERMES spectra and get good stellar parameters on them to identify our target stars as solar twins. And that's where my work is coming in. I developed the EPIC algorithm in our last two years, which utilizes existing GALAH data to create a model to determine stellar parameters fully differential with respect to a very high precision sun spectrum. And the way it works is that we use a spectral library from Thomas Witter in 2018, created by Thomas Witter in 2018, which is medians of observed spectra, which is created with GALAH DR2. As the basis of our model, we have a solar reference spectrum, which we use to analyze all of these spectra. And on the right here, you can see a little diagram that shows the fundamental steps of the algorithm. First, we plug in our spectral library into our analysis. We analyze about 130 different absorption features. We model these features with the spectral library at hand. And if we then later apply our model to target spectra of unknown stellar parameters, we can get the stellar parameters back from which we can determine if the star is indeed a solar twin or not. So I mentioned that it's differential, and I didn't talk about that a lot yet. And so the reason why we use a solar reference spectrum is that it makes a few steps a lot easier and lowers the systematic errors because of it. For example, it's way easier to find the continuum for the reference spectrum and then set our target to the level of to the same continuum than to measure the continuum in our target spectra directly, which lowers our systematic errors. So with this method, the first thing we had to test was how well we actually matched the data at hand, so the GALAH DR2 data. And for that purpose, I have a plot here showing the metallicity on the x-axis and the metallicity differences between the GALAH DR2 metallicity and our metallicity on the y-axis. This data set was about 2,000 stars that we just photometrically selected as if we wanted to find solar twins. So they are solar-like in a way, which you can see here, the metallicities are very solar-like. And as you can see, it's mostly statistical noise that we have around a difference of 0, which means that these agree very well. The red line here just shows a little offset we had to do in order for our data to match the actual solar values, so that the sun actually has solar metallicity, which we found necessary. Which is, so if you look at it, you should look at fluctuations around the red line instead of the 0 line. So you might ask, well, what are these uncertainties? I mentioned at the start that our uncertainties are very important when identifying a star as a solar twin. And we have a target signal noise ratio of 25, at which we want to achieve very good, reasonable uncertainties. And as you can see here, our average uncertainties plotted against the signal noise ratio is always below 0.04, and at our target signal noise ratio, it's about 0.03, which means that we are comfortably below our uncertainty limit, which we set at 0.1 dex of metallicity. And for comparison, the GALAH DR2 uncertainties are plotted up here. The average uncertainty is plotted up here in the red dotted line, red dashed line. So let's talk a little bit about our the targets and our observing. So we wanted to observe with HERMES because it can observe a lot of targets at the same pointing. We came to the telescope with about 540 solar twin candidates in the same field, all of which are pretty faint, from 15.4 to 17.4 in the G magnitude. We predicted that for our faintest targets, we would get a signal noise ratio of about 5.9 for our faintest targets when we have a 1 hour exposure, which means that to gain our signal noise ratio of 25, we need about 18 exposures to combine them into such a spectrum. And our aim for this whole affair is to get about 50 solar twins, solid solar twins, that we can follow up with the VLT afterwards to get good ESPRESSO data that we can use Daniel's method to determine alpha on. So we had an observing run which ended just last week. We didn't have great luck. It was actually snowing at the AAT. We had about 3.5 nights where we could get data out of the 9 half nights that we got. And yeah, but our data actually turned out quite good. So for our faintest targets that you can see here, the signal to noise ratio that we get is about 5.9, about what we predicted, which made us very happy because, well, even though everything went wrong with the weather, our data actually was very good. And for the whole 3.5 half nights that we had during that we had in effective observing time last week, we actually combined them into spectra that are almost matching our signal to noise ratio target of 25 here. So obviously the lower bins here got more observing time, which is why you see these jumps. And even for our lowest, for our faintest targets, we are almost at a signal to noise ratio of 25. We still have a little bit of observing time to go. We will have another run in the start of July for another 5 nights. And we think that we can push most of these stars over our signal to noise ratio of 25 and actually make them usable data for us. So to conclude, we actually proved that you can observe these very faint targets with HERMES, and you can gain reasonable signal to noise ratio of 25 of them. We have an algorithm that can use these spectra and determine stellar parameters, and therefore also get the information if these stars are solar twins, confirm these solar twins. And with that, our campaign to observe with HERMES is almost at an end, and we hope that we can apply for VLT ESPRESSO time soon with our best targets at hand. Yeah, thank you for your attention, and I'm ready for questions now.
All right, thank you very much, Christian. It's very interesting stuff. It's what I like about this is it's partly very familiar, sort of solar twins, differential analysis, the sort of observer stuff, getting snowed on when you're trying to observe, all that stuff that we all, in the stellar community, yeah, we feel that. But it's also this very other purpose that when we were planning GALAH, we did not consider what the data set could be used for looking at fine structure constant variations. So I find this really exciting. Do folks have questions that they want to ask Christian about the project? Oh, Michael Hayden is in the chat. Michael, do you want to talk?
Yeah. So hi, Christian. Very nice talk. It should be a good sample. So when you did the target selection, did you take extinction into account? Because at 4 kiloparsecs away in low latitudes, it could obviously impact what stars you select.
I actually don't know. Like I'm not the person who did the target selection was done by Fan Liu. I have a rough idea how he selected them, but I don't know if we took extinction into account. Sorry, I can't answer that.
So yeah, I guess if you didn't, it might be good just to analyze even the data you have. If it's signal noise 20, you might be able to get temperatures out and just see how well you did.
Yeah, I can maybe just add a little bit to the answer there. I'm Michael Murphy from Swinburne, so I'm leading this program. The selection was done so that the targets were about 30 degrees off the plane.
Okay, yeah.
So dust is not a big issue. We very carefully selected the fields so that they had as low dust extinction along the infinite line of sight as possible. So there's probably hardly any dust in between us and the stars. So the idea is to try and make sure we're getting we're not confused. We're not confusion limited. We know we're observing which stars we're targeting, and also we're not affected by dust.
Yeah. All right.
Thanks for the clarification there. Paula, do you want to ask a question?
Yeah. Hi. Very, very interesting. I was wondering if you applied them for espresso time. I mean, what is the kind of quality for the data you would like to have? And I am also not very certain what kind of things you'd like to derive from the spectra that could, like, how does it work with this method to studying this issue of the hyperfine structure constant?
Well, the method that you're mainly asking about, the method to confirm solar twins, or to
no, after. I mean, okay, now you have confirmed these are your best solar twins, and then you want to go and observe with espresso, but I'm not very sure what you want to do. What kind of data what signal to noise, and what are you going to derive that you cannot get from the spectra that you already have?
So the fine structural constant part of this project is mainly the work of Daniel Berkey. He looks at, to determine the fine structural constant, he looks at separations of absorption lines. We need a very stabilized spectrograph in order to get these separations very precisely, which is why we want to use ESPRESSO for it. We want to map out alpha throughout the galaxy, which means that we want to go further into the galactic center. So we want to have these distances, further solar twins. And the reason why we use solar twins for that is because we can't just directly take the wavelengths of absorption features from the laboratory and go to a star and apply them. That doesn't work, not to the precision that we want. But it works if we compare absorption features that we have in the sun compared to a solar twin, because these stars should have very, very similar spectroscopy, and therefore we eliminate a lot of systematics by just comparing these two stars. I don't know if that answers.
Yeah, and would you then do kind of a direct comparison of the spectra? So you would take a solar spectrum with ESPRESSO, or you would take one that is in the archive or something like that, and then you would compare directly. You won't derive abundances or anything like that, just the comparison and see where these lines lie, right? To see if the spectrum is stretched or something like that.
Yeah, so the line, if the fine structure constant were to vary, then we would notice very slight shifts in these absorption features compared to each other.
Oh, that's beautiful. Beautiful project. Congratulations. I hope it works, that ESPRESSO gives you the time.
Thank you.